Hi everyone, we are here at the University of Illinois campus in the Siebel Center for Computer Science. That's the Department of Computer Science. And today we are talking with someone who is an expert in SDNs, or software-defined networks. And we are here with Professor Brighten Godfrey, who's going to tell us more about SDNs.
Hi, so thanks for having me, Andy. So my name is Brighten. I'm a professor in computer science here. I've been at the University of Illinois for about 5 years. And before that, I was at Berkeley, where I did my PhD with Jan Stoika. And before that, Carnegie Mellon. So now I am in the systems and networking group here. So I work on a broad range of things within networking and theory of networks. So including algorithms and software-defined networks, network verification, data centers, and the wide area internet.
So can you tell us a little bit about what software-defined networks are?
We have networks that work reasonably well because we have, these brilliant masters of complexity who can deal with that level of complexity to run a modern network. What the vision of software-defined networking is that that structure of network needs to be refactored and abstracted. And there's, I would say, 3 key features that you would find in a software-defined network to achieve that goal of programmability. The first is a well-defined interface to the switching hardware. So what we would call the data plane, where packets go into a box and they are, inspected and processed and sent out. So that involves, looking up a destination in a table, maybe doing access control on packets, some kinds of packet filtering, basically the fast path of processing packets. That's what you have specialized network hardware for, is handling data flow through the network quickly. But the idea is we want a low-level, well-defined interface to that fast hardware. And that piece of SDN is today embodied in the OpenFlow protocol. But it wouldn't have to be the OpenFlow protocol, and even OpenFlow itself is evolving. So we've got an interface to the data plane. If we have that interface, what we can do is lift out the intelligence from the individual boxes and centralize it. So we have a central controller or multiple controllers that are coordinated as a distributed system, but a logically centralized controller that's now going to define the policy and push it out to the switching gear. So that's the second key abstraction, is this idea that we can centralize the intelligence. Once we have that centralization, then the third idea is that we can build programming abstractions that help us orchestrate that whole network. Right? So the sort of minimal level of this would be that in a network operating system, if you will, that's running on the central controller, will take care of building a picture of the topology, snapshot of the topology, and presenting that to a higher level application. And then it will also take care of, once a decision has been made about how to handle data flow, pushing that out to the devices in the network. And then you can think about higher level abstractions, and this is where a lot of the interesting research has been, of how would you make networks easily programmable? Do you need a new programming language? Do you need libraries for doing certain kinds of computations? How do you structure network programming? So that's kind of a quick overview of these, some of the key features that you find in an SDN. And it's a term that it is sometimes overused and applied in different ways. But those 3 key features are part of what I would say is the consensus vision, that you have a well-defined interface to the data plane, you have the ability to centralize intelligence, and then you can build higher level policy abstractions in that centralized controller.
So from what you described, it seems like the collection of routers and switches in the network, they behave as a distributed system with maybe a central controller or a distributed controller. Does that mean that distributed algorithms like the ones that the students are learning in the class, things like consensus, Paxos, those are now directly applicable in SDNs?
Absolutely, yes. In fact, they're already used in deployed controllers because you like this abstraction of a single centralized controller. So that's how we like to program. It's easy to program, a single app, single-threaded, has one view of the world. It's not a distributed system, but that, of course, is a lie. It is a distributed system, and you can't have just a single controller because it would be unreliable, right? So the single controller can fail. The connections between controllers and switches can fail. The network itself can become partitioned, and then that controller is going to be on one side or the other side of a partition and wouldn't be able to control the gear on the other side, right? So if you look at production deployments, like, for example, Google's deployment of SDN in their wide area backbone, it's a distributed system all over the place in every layer, including the switching gear itself, where there's very interesting questions of timing of events that you install into the switching gear. Like, I asked the switch to start dropping these packets or sending these packets over here, and I asked this other switch to do something else. But I don't know exactly when those events are going to happen. And so you get into consistency problems within the network itself that might manifest in packets going in a loop, or a service being unreachable, or potentially even worse, if maybe leaking out sensitive data if you don't take care to understand that the switching gear itself is a distributed system and you don't have good control over the timing. And in the controllers, in production deployments, like I said, there are replicated distributed controllers that run algorithms that I'm sure your students are learning, Paxos and other variants, to build a consensus view of what the network is, so that you can then write a policy on top of it and install it into the switches.
And are SDNs applicable only to the wide area network, but or also to data center networks themselves inside the data center?
Yeah, that's a good question. So I think there's a lot of excitement around SDN, and there's a vision that SDN will be everywhere, right? And that may be true, but one question is, what are really the killer applications that are going to drive early deployment? And I would say there are two applications that, at least, that have become really valuable. And one is in the wide area and one is in the data center. In the wide area, and a good example is Google's wide area backbone, these are very expensive networks carrying huge volumes of data between large data centers, for example, 12 or 13 sites in Google's network. And so optimizing that flow of data very carefully has a huge amount of value because the cost of sending it and the volume is so high, right? So having the ability to do optimization of that data flow, programmatically, of course, is really valuable, right? And using traditional algorithms in gear, it would be very hard to just say abstract away the data flow and plug it into some optimization package like a linear program solver to find an optimal flow of traffic, and then plug that into the network. But once you've gone to the significant amount of work that it takes to build an SDN, then you can do that. Then you can say, all right, here's my traffic flow. I'm going to optimize it. This is exactly what I want to happen. Program the switches, and you're done. So that's a wide area app. Now, in the data center, a killer app that's been there that's gotten a lot of traction is virtualization of the data center. So you want to be able to dynamically provision virtual networks, such as for a tenant within a data center, that are isolated from other virtual networks, and that present to that tenant, when you're renting space in a cloud, you want it to look like your network, and potentially even, a network with certain functionality or topology, but just at a minimum, you've got a collection of virtual machines, and you want them to be connected on some virtual network, and those virtual machines may actually be behind the scenes moving around, and the virtual network can be moving around. So orchestrating that dynamic provisioning of virtual networks in data centers has been one of the early applications of SDN.
So software-defined data center, software-defined storage are new terms that are coming up right now. Do you think there are lessons that can be learned from software-defined networks that can be applied to these areas?
The ability to think of the whole data center as sort of one organism, and develop effectively an operating system for a data center I think that's the idea that these different research and industry thrusts are pushing at, right? So instead of having a monolithic operating system on each individual router and switch that has all its intelligence there, now we're thinking about the network as one cohesive unit that we want to coordinate, right? And then we have to think about traditional distributed systems issues. We have to think about traditional operating systems issues like resource isolation and task scheduling. And bringing these together with other parts of the data center, storage and compute, and then thinking about that whole together, that's a pretty interesting direction, actually. So I think we're going to see more and more work on, for example, jointly coordinating and optimizing flows in the network along with placement of VMs and applications, for example.
So I want to return to something that you mentioned earlier, which is data center topologies. And I know you have done quite a bit of work in that area. Can you say a little bit about the work that you have done in data center topologies?
Sure. So now some of our research has been on thinking about how you structure this topology of the network. And there's a couple problems with a fat tree-like design. One is that both the fat tree and a number of other structures that have been proposed, topologies that have been proposed, and there are many of them, are rather inflexible because you're building a very specific structure with certain numbers of switches that are connected in certain patterns. And so if you're incrementally expanding your network, or if you want to use heterogeneous components, right, you get upgrades, then how do you build it? What does your network look like? And it can be very inconvenient to either restructure it or to maybe leave ports free for later expansion, but then you're wasting capacity.
Right, so scaling is hard.
Scaling is hard. Scaling is hard. And then another problem is just that, well, you'd like to be as efficient as possible. These networks are very expensive because they're provisioned for worst-case traffic, right? So these are not cheap networks. So what we looked at was taking a step back and said, okay, well, if these rigid structures are rather inflexible, hard to scale, what if we get rid of structure completely? What if we build a network out of a random graph? And this sounds a little bit crazy at first, because you have no idea what you're going to get. Why would you take this data center that you want to be highly reliable and high performance, and just completely randomize its network so it looks like a bowl of spaghetti. The first reason for doing this is that it's extremely flexible, right? So if you want to expand your network, it becomes, adding a switch and doing a few random swaps of links, and you're done. If you want to use heterogeneous components, no problem. Just throw it into the mix, randomly wire it in, and you're done. So that's a clear advantage, and you can quantify that and get, show a clear cost savings. Now, a surprising thing is that, okay, what happens to performance? Do you do worse? How much worse do you do when you completely randomize this topology? And the answer turns out to be that the random graph gets higher performance with the same equipment by roughly 25 to 40%. And that's kind of a counterintuitive result, that you can take these carefully structured networks that people have been using and designing for decades, not only in data centers, but going back to high-performance computing. And there's more and more connections between HPC and data centers. You take these networks that have been very carefully designed and structured and completely randomize them, and you get better performance. That's kind of a counterintuitive result, but what it stems from is the idea that is sometimes called 6 degrees of separation. Okay, that when you're in a network that has randomness, like a social network, like people we know, you're connected by very short paths with basically anybody else. And the reason is that the connectivity is very diverse. The connections to other nodes in the network are very diverse. So diverse connections means that you can reach a large number of people in a small number of hops through this network. Same for the data center network. You can reach servers on average in fewer hops. So if you have shorter paths in terms of number of switches that you have to traverse, then you're using less network resource to send the same packet, right? If I go 2 hops instead of 4 hops, I'm using half as much bandwidth. So that means that you can support more servers with the same equipment.
Would you also say that a random network costs less to build than a factory network where you have some very high-powered servers or switches?
The goal is that you can have higher performance with the same equipment, or you can have the same performance with less equipment, right? So you can choose to use fewer switches, fewer links. And there's a lot of interesting questions here. I'm making it sound kind of simple, but there's some big questions about how do you cable up this complex topology? Is that going to be difficult? Are you going to get consistent performance with an unstructured network? How do you do routing in an unstructured network, and how do you do load balancing so that you can really extract all of the value from that potential bandwidth? So those are systems design questions that are good questions, and we've solved those problems, but there's interesting stuff in there. The routing in particular connects with SDN. So this is a good example of where you can use SDN for routing. If you use traditional means of pushing data through a network, you don't actually get a great load balance, especially with a complex topology. So it's particularly for this random network, for this jellyfish design, as we call it. In the jellyfish network, you can use SDN to great advantage because you can do better traffic optimization, and it makes a particularly big difference in this unstructured network.
Where do you think software-defined networks are headed in the next 5 years?
Those are big questions. So for software-defined networking, I think what's particularly interesting is how do you build this operating system that makes programming networks convenient? And I feel like we're just scratching the surface. There's some interesting work on programming languages for networks, but there's many different possible programming languages. Do you need a programming language? Do you need good libraries? Should you think about maybe using a database-like interface to a network, which is something that one of our postdocs here, Anduo Wang, is exploring. The question of how you build these abstractions that make networks easy to program, so you can basically you can control a network in an intuitive and powerful way, whether that's optimizing traffic or responding quickly to security threats. I think that's going to be a really interesting space. And both in research and in industry, there's a lot of uncertainty about what those controllers are going to look like. I think the general vision towards opening up an interface to the data plane and centralizing that intelligence is a direction that's pretty clear. But then how we make that programming convenient and powerful is, and what particular controller implementations are really going to take off in industry. Those are big open questions that we're going to sort out as a community over the next 5 years.
My last question is more about how it feels like to work here at the University of Illinois, and also working at your startup company. What does it feel like here?
So UIUC has been a great place. The best thing about being a professor anywhere is getting to work with students, and we have great students here. Sitting down with students and just talking for a couple hours at a whiteboard about ideas, and then going home and thinking about something in the shower, and you get an idea and you come back and talk to your students the next day. That's a really fun process, and seeing that over time. When you start in research, it can seem hard to make progress. But then if you keep, persistently plugging away at it, and then look at what you've done, over a period of a year, then you can see, hey, I really did something new. And the process of doing that for myself when I was a grad student, and now also, seeing that happen and seeing students get excited about research has been great. So I love teaching. We have great students and great colleagues, and you're getting to teach a lot of students. So you're particularly lucky.